Today we want to continue the study of second order differential equations that are of the form that I have here: y double prime plus p of x y prime plus q of x y equals f of x. And well, we made a first video regarding this topic when we saw that, well, a general solution for this differential equation can be written as, well, the sum of two functions. One is for the homogeneous version of this equation. You take this expression and take it equal to 0, and then, well, y sub h is going to be the solution for that equation. And then we get a particular solution that will involve f of x, just to generate, well, the complete solution for this differential equation. So in the first video, we deduced the method of variation of parameters to solve these kind of equations. And we saw that, well, if, for example, we have a solution for the homogeneous equation, y sub h equals c1 times y1 of x plus c2 y2 of x, where y1 and y2 are linearly independent functions. Well, we saw that we can establish a particular solution given by y1 of x times u1 of x plus y2 of x u2 of x. Okay, and, well, the mission was to find u1 and u2. And, well, we saw that in order to do that, well, we deduced the variation of parameters method. And we got the next, that u1 of x is equal to negative the integral of y2 of x f of x over w, and u2 of x is equal to the integral of y1 of x f of x, and I forgot a dx here, f of x dx over w, where w is the Wronskian of y1 and y2 given by the determinant of this. Okay, so given that y1 and y2 are linearly independent, well, this guarantees that the Wronskian is going to be different from 0. And also, to be more specific, well, we are going to find a solution yp that it will be valid on the interval x0, x. Okay, so that means that, well, we are going to rewrite this as u1 of x equals to negative the integral of, well, the integral from x0 to x of y2 of t f of t dt over w, and u2 of x is equal to the integral from x0 to x y1 of t f of t dt over w. Okay, and, well, looking to this expression, well, we need to multiply u1 by y1 and u2 by y2. So we are going to get that yp is equal to negative y1 of x, the integral from x0 to x y2 of t f of t dt over w, and this is, well, it's going to be the sum, and y2 of x, the integral from x0 to x y1 of t f of t dt over w. Okay, well, we see that, well, we have two integrals that have the same integral limits, and it's under the same variable, which is t. So we can put together these two integrals to get the next. This is equal to the integral from x0 to x of negative y1 of x y2 of t f of t over w plus y2 of x, y1 of t, f of t over w, and then we close the brackets and dt. Now we here see that we can take the common factor f of t and take it out from the brackets. We are going to write it here, and then this function that we have here, which is a function of two variables, x and t, this is what we are going to call the green function, okay? In honor to the mathematician George Green. Okay, so we can rewrite this as the integral from x0 to x of, a function of x and t times f of t dt. And remember that f of t, is the function that we have here in the definition of the differential equation, but evaluated at x equals t. Okay? Okay, so now we have defined the green function, which is, defined in terms of a differential equation, okay? So g of x comma t is equal to, negative y1 of x, y2 of t, plus y2 of x, y1 of t, all over w. Well, this is the important result for this video, the green function. In this case, I think it is worth it to rewrite again the definition of the Wronskian. And here we are going to establish that the homogeneous solution is c1y1 of x plus c2y2 of x. Well, this is everything we need to define the green function. That's why I rewrite it. So if you have this green function, you need to know that y1 of y2 are linearly independent solutions that compose the homogeneous solution for the second order differential equation. And the Wronskian is, it is taken for y1 and y2. So now we are going to see a quick example of this. We are going to find the solution of the differential equation y double prime minus y equals e to the 2x. Okay, so in the method of variation of parameters, we first need to find the homogeneous solution. Okay, we need to find y's of h. Okay, so to do that, we establish the homogeneous equation, which is y double prime minus y equals 0. Okay, in that case, we see that y double prime is equal to y, and just by the form of this equation, we immediately see that the solution is an exponential function. Actually, we have two solutions that are going to be of the form c1 e to the x and c2 e to the negative x. It is not very hard to notice that, these two functions are solutions of this differential equation. So the homogeneous solution is going to be, the linear combination of e to the x and e to the negative x. That is c1 e to the x plus c2 e to the negative x. Okay? And we easily identify that this can be defined as y1 of x, and this can be defined as y2 of x. Okay? So here is where the most interesting thing comes. We know that, the particular solution will have the form u1 of x times e to the x plus u2 of x times e to the negative x. And other thing is that, we can find the green function, okay? Because we already know y1 and y2. So first of all, we need to calculate the Wronskian, and that is the determinant of, e to the x, e to the negative x, here we are going to write the derivative of e to the x, which is the same, and here we have negative e to the negative x. If we do this, we are going to get, well, negative 1, because e to the x times e to the negative x, well, it gives you 1. And the negative, the same, negative 1. And this is going to be, well, negative 2. Okay? So we can go to the definition of the green function to see that we need to write negative y1 of x, y2 of t. Okay, so that is negative e to the x and e to the negative t. This is y2, but evaluated at t. And then plus, well, y2 of x times y1 of t. Okay? So we get e to the negative x, e to the t, and then over the Wronskian, which is negative 2. So this is going to be e to the x, e to the negative t, plus e to the minus, actually, e to the negative x, e to the t over 2. And this is, well, g is going to be, well, e to the x minus t minus e to the t minus x all over 2. That is the green function for this differential equation. And actually, we'll see that it will be convenient to rewrite this as negative x minus t just to have the same exponent, because now, well, we are going to use a definition that, well, this is equal to the hyperbolic sine of x minus t. This is a very, well, famous definition in hyperbolic trigonometry. So we can say now that, well, yp is going to be equal to the integral from x0 to x of, well, the green function, but our green function is sine h of x minus t, and times, well, f of t dt. This will be the particular solution to the differential equation. Okay, this is if we follow the formula that we got, but recall that in our example, f of x is e to the 2x, okay? And our formula says that we need to take that function but evaluate it at t, okay? So f of t is going to be e to the 2t. So we get that the particular solution is going to be the integral from x0 to x of sine, the hyperbolic sine of x minus t times e to the 2t dt. And, well, yeah, in this case, looking that our function f of x was an exponential function, well, yeah, it turns to be more useful to use this definition on the particular solution, okay, just to be able to multiply the exponentials. So we get that yp is equal to the integral from x0 to x of e to the x minus t minus e to the negative x minus t over 2 times e to the 2t dt. Okay, so if we work on this expression, we are going to get the integral from x0 to x of e to the x minus t plus 2t is going to be plus t minus e to the negative x plus 3t all over 2 times dt. If we keep working on this integral, we are going to get, well, 1/2 of e to the x times the integral from x0 to x times e to the t dt minus, well, e to the negative x times the integral from x0 to x of e to the 3t dt. Okay, so this is going to be equal to 1/2 e to the x minus e to the x 0. Okay, then minus 1/2 of e to the negative x, okay, times 1/3 e to the 3t. Well, we are going to evaluate this. This is going to be e to the 3x minus e to the 3 times x0. Okay. Okay, so well, now just by simplicity, let's take the interval x0 comma x to be the interval 0 comma x. So we are going to change x0 equal to 0 to get that y sub p is going to be 1/2 of e to the 2x minus 1/2 e to the x, then minus 1/6 times e to the 2x, and then plus 1/6 e to the negative x. Okay, and if we simplify, well, we are going to get that this is going to be 1/3 e to the 2x minus 1/2 e to the x plus 1/6 e to the negative x. Okay, so just to finish, we can say that the solution to that differential equation is going to be y equals y sub h plus y sub p, and that is c1 e to the x plus c2 e to the negative x plus yp, which is the function that we just found, 1/3 e to the x, e to the 2x, sorry, and minus 1/2 e to the x plus 1/6 e to the negative x. So this is a very simple example of how to use the concept of green function to solve a second order differential equation. So that solution that we found is the solution for this equation, and recall, the tool that we introduced is this, the green function, to solve this kind of differential equations.